Talk about multiple stage experiment. So what we learned last week is we do one trial, okay? Toss a coin, throw the dice, like we do one thing. So this exercise is talking about we do multiple stage experiment. For example, I toss the coin twice, okay? One time and then another time. So we have two things we will go through today. So the first thing is the table, okay? I think we have seen this table before. So there's a table and also tree diagram. Okay, table or tree diagram. That's the technique we use to go through multiple stage experiment. But like obviously tree diagram is more like normally we'll use tree diagram because the use of the table is very limited. First of all, to use the table, it can only be two stages. Okay, it can only be a two stages experiment. And the second requirement is each stage, the event must be equal likely. The outcome must be equal likely. Okay, that's the two requirements when we can use the table. For example, I have a bias coin. I want to toss it 2 times. We can't use the table because it's not equal likely outcome. With the probability I get head or tail is not half and half, so I can't use the table. So table is with restrictions and a lot of restrictions. Only 2-stage experiment. If I toss it 3 times, I can't do by this way. And equal likely events, okay, equal likely events. And tree diagram can deal with any multiple stage questions, and also in VCE this is still quite important. Okay, still quite important. We'll still use tree diagram to deal with some even really hard questions. Okay, tree diagram is still very popular to solve questions. So let's have a look at the table first. To use the table, we have, well, with replacement and without replacement. Well, something is naturally, well, when I say with replacement, without replacement, you know that. For example, I'm drawing card from the box and I say with replacement or without replacement, I will tell you that. But for some events, it's naturally with replacement or without replacement. For example, like throw the dice or toss the coins is with replacement, because when you get ahead, you can still get ahead for the next time. You haven't taken out from your outcome. You haven't taken out from your sample space. But for example, if I said, I also talk about the probability. Well, say if I have a mix of boys and girls in the class, and I also pick a team with 2 boys and 1 girl. This will be a without replacement case because 3 people, it can't be replaced back and take him again. Like for example, I take someone first and then I can't replace you back, and then still a chance I can pick you again for the second time, and then you can't form a group of 3 by yourself. So that's naturally a without replacement case. Or say I pick a chocolate from the box and I eat it. Okay, I have eaten it. I can't eat the same chocolate twice. So that's a naturally without replacement case. So sometimes it won't be that obvious to tell you with replacement or without replacement. You need to decide by yourself. And most of the case, you need to decide by yourself. Okay, but for example one is kind of easy. It said without replacement already. So 2 letters are chosen from the word KICK, without replacement. So you won't pick the same card twice. Okay, you won't pick the same card twice. So without replacement question. Well, twice. Okay, so it's and also the probability to take each card will be equal likely. Even though I pick one and then put it away, we're left with 3 cards. It's still equal likely for the second time we select the card. So a third, and a quarter for the first time, and a third for the second time. So it's still equal likely events. But because it's without replacement, I won't have result for those boxes because I can't select the same card twice. Okay, I can't select the same card twice. We will have on one diagonal there's cross. Well, I can't have it twice. Okay. Also, well, in the book, I think they give away, like say, which is the first selection, when is the second selection. But I don't care that much in this case. As long as you pick which one is the first one, which one is the second one, and you're all doing in the same order, that will be fine. For example, I like the column to be the first selection and my row to be the second selection. So when I write my, well, you can do the other way around. But when, for example, the one I did here, I write my results. I will write IK, CK, and KK. Okay, so the column always needs to be the first one. Okay, like the first element. Well, for this one, it will be the same. It will be KI, CI, and KI. Okay, so it's always the first to pick the column and then the row. So later we have KC, IC, and KC again. Well, for the last one, I will have KK, IK, and CK. I still can have 2 Ks because we have 2 cards. Okay, I still have 2 cards. I pick one and then I have another one to pick. So that's why I can have a repeated KK there. Also, let's say this is the first card, then this is the first card. That's why we have a cross here. I can't pick the same card again. But this is the first, but this is the second. I can take the first card and then second card. That's no problem. Same as the KK here. Okay, same as the KK here. So now, well, because each selection is equal likely, so your overall outcome will be equal likely as well. Okay, your overall outcome will be equal likely as well. So I just count how many outcomes do I have. Well, I won't count the cross because there's nothing achieved. So in total, I have 12 outcomes. Okay, in total, I have 12 outcomes. So there are 12 outcomes. Okay, 3 in each column, and there are 4 columns. So I have 12 outcomes in total. Now let's have a look at B. B is asking you find the probability of obtaining the outcome KC. Okay, the outcome KC. So when I write things in the bracket, always describe the first K and the second C. That's with order. So when the thing's given in the bracket, like in the coordinates form, it means with order. So it can't be a C and a K. Well, it really depends on do I care about the order. Do I want a first C and a second K, or a first K and a second C, or do we just want the K and the C in my hand? Or if I just want the C and the K in the end, I don't care about the order that much. But in this question, it gives you the coordinates, which means you must follow the order. Okay, you must follow the order. So KC, you can only have one KC here. Okay, the first K, second C, that's unique. Okay, unique. So that's 1 on 12. Okay, 1 on 12, because only one outcome give you what you want. This is your preferred events. Like I can say, well, how I can write the notation. We should learn notation now. The probability of achieving KC that equals to 1 on 12. Oh wait, there's a second one, right? Oh, there's 2K. There's another one. Yeah, 2 over 12. That's 1 on 6. Sorry, not 1 on 12. So 12, 1 on 6. I have the first K and the C, a second K or C. So I have 2. Well, the probability of selecting 2 Ks, well, I can say probability, well, I can write KK. Okay, I can write KK. Even though it says with order, but like which K I get, I don't really care, like KK. I can just write probability of KK. That's 2 on 12 as well. That's 1 on 6. Okay, and the KK is here and here. And the third one, I want a K and a C. Okay, I want a K and a C. So this case, I don't mind whether K first or C first. I just want a result with a K and a C in my hand. So I can write, well, if I want to use math notation, I can say KC union CK. Okay, I can represent in that way. So what result I want either KC or CK. So I use a union in between them. So this or this will be fine. Okay, CK. You have 2 CKs and 2 KC. That's a 4 on 12, which is a third. Okay, which is a third. So we use the union to connect two outcomes when we want both of it. Okay, when we want both of it. So we use the union to represent. Okay, that's the first example, and let's have a look at the second example. Okay, second example is with replacement. Okay, with replacement. Well, it doesn't say with replacement, but when you throw the dice, it definitely is a with replacement case. You get a 1, and you can still get a 1 for the second time. You haven't taken that outcome outside your sample space for the first time. So for this table, okay, for this table, I've got like, well, I can say this is the first. This is the second. Okay, you can do another way around. First in the row and second in the column. The total number of outcome must be a 36. Okay, the total number of outcome must be a 36 because there's no cross on the diagonal. You can take all the outcomes. Okay, without, well, I don't want to really fill in that table like 36 numbers. It's not that fun. But find the probability of obtaining the outcome 1, 5. How many 1, 5 do you think you get? 2 or 1? 1, 5 means with order. Okay, with order. 1 first and then 5. 1 only. Okay, you can only one case to get a first 1 and second 5. There's no second time you can get the same thing. So the probability of 1, 5 give you 1 on 36. Okay, there's only one such outcome. Okay, the second one asks you the probability of doubles. How many doubles do you have? 6. 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. So that equals to 6 out of 36, and that's a 1 on 6. Okay, second one, the sum at least 10. Well, if you can see the table, sum of at least 10. Well, think about the sum. If I get, first time I get a 2, is that possible to get a 10? What the minimum number I should get in my first try? 4. Okay, so the first one I must get a 4 to give me a 6. Okay, that will give me a 10. Or I can get a 5. I can get 5 and 6. Or I can get a 6, get me 4, 5, and 6. Right? So they are the outcomes that can give you more than or equals to 10. So I have 6 such outcomes. Well, 4, 6, 5, 5, 5, 6, 6, 4, 6, 5, and 6, 6. So that equals to 6 out of 36 and equals to 1 on 6. Okay, a sum not equals to 7. Are you going to count the sum not equals to 7? What do you count? Give you 7, right? Give you 7. So 1, 6 will give you a 7. 2, 5 give you a 7. 3, 4 give you a 7. 4, 3 give you a 7. 5, 2 give you a 7, and 6, 1 give you a 7. There are 6 outcomes. Give you 7. So there are 30 outcomes. It's not going to give you 7. So it's a 30 out of 36, and there's a 5 over 6. Okay. So this is the probability of A equals to 1 minus probability. Well, probably A not equals to 1 minus probability A. So I want the probability of 7 not. That will be probability 1 minus probability giving you 7. Okay, giving you 7. Well, sum equals to 7. So I'm using this formula. I can use this formula by like 1 minus 6 out of 36. That's the probability give you 7, and 1 minus that is the probability not give you 7. Okay, not too interesting here. Have a look at number 3. Number 3 is find the probability that when a coin is tossed 3 times, one head is observed. Okay, so because it's tossed 3 times now, table's not going to work. Okay, table's not going to work. So what will work is only tree diagram. Okay, it's only tree diagram. So how we can do the tree diagram? Okay, that's a tree diagram. So the first one, the second time, and the third time. Okay. Well, I just go from backwards because I know how many outcomes there should be. So I just go backwards. It's okay, I'm waiting you. So they are all equal likely outcomes. Okay, they are all equal likely outcomes because it's the same chance to get head and tails. My question is, how many outcomes only give you 1 head? But when say not to count the tree diagram, three outcomes, okay, either head or tails. How many will give you only 1 head? Well, head can be here, head can be here, head can be here. The other 2 is tails, right? Head, tail, 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 head, tail, 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 head, right? That's what you will get. That's with 1 head. So there will be 3 outcomes. Or you can count for it. Okay, this one will give you 1 head. This one give you 1 head, and this one give you 1 head. So that's the case when you have three outcomes with 1 head only. So the probability of 1 head equals to 3 out of 8 because you have 8 outcomes in total. So you have 8 outcomes in total, so it's 3 over 8. B, at least 1 head is observed. How many outcomes will be at least 1 head observed? 7, right? We'll have no head observed. It's all tails. Tail, 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 tail. So it is probability at least 1 head equals to 1 minus the probability of all tails. And that gives you 1 minus 1 on 8, and that's 7 on 8. Okay, just exclude the case that's no head at all. That's 7 on 8. C, the second toss results in a head. Okay, the second toss results in a head. How many of them? 4 is, well, that's the second tail with head, that's the second tail with head. So I have 4 outcomes there. Okay, that's 4 outcomes. But because your second toss can only be a head or a tail, so it's half the chance. Okay, half and half. That gives you a half. That's 4 on 8. Okay, that gives you a half. All heads or all tails observed. Okay. OH union all tails. Because the word or gives union. Okay, gives union. So we have 2 such outcomes, so it's 2 on 8. That gives you 1 on 4. Head, 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 tail, tail, tail. Okay, that's used. Well, this is a very simple tree diagram. It just needs to make the count carefully. Okay, let's have a look at example 4. Can you set up a tree diagram for me, please? Okay, box A and box B contain 4 counters each. Box A contains 2 red, 2 green, and B contains 1 red and 3 green. A box is chosen at random and then a single counter is selected. For your tree diagram, what you will do for the first selection? A and B, what's the probability? So we have half and half here. Okay, for box A, what do you get? Red and green, so what's the probability? Half and half. Okay, for the second one, what do you get? Okay, what's red? A quarter, and the green is 3/4. Okay, so that's the tree diagram. So I can have box A a red, box A a green, box B a red, box B a green. So I have a quarter of this, a quarter of this, 1/8 of that, 3/8 of that. Well, you add up everything should give you 1. You add up should give you 1. That's the result and that's the probability of that particular result. This is not equal likely events anymore. Okay, this is not equal likely events anymore. So, what's the probability of selecting box B and a red? So that's the probability of B comma red. Okay, so select B and the red. So it's the probability of B comma red. So that will give me 1 on 8. Okay, that will give me 1 on 8. What is the probability of selecting a red counter? So that's the probability of red. Okay, that's the probability of red. So I can have a red. Well, I just want a red in the end. I don't mind which box I select that. So it can be from box A or from box B. So, which is, yeah? You have music? Okay, I have red from box A and red from box B. So I have 3/8 for that. Okay, 3 on 8 for that. So do you care about which box it's coming from, or do you care about the color? Just the color. So if it's just the color, it came from both boxes. Okay, it came from both boxes. Alright. Last example. Okay, last example for today. Well, there are 5 people participating in an event. 2 awards will be given to 2 people randomly. Cannot give 2 awards to the same person. Okay, I can 5 of us, and you 2. I'll give you, and it can't be you again. So I can get the second one, or anyone else can give the second one. So it's all random. What's the probability that person A will win one of the awards? Well, I don't mind which awards I win. Just for example, I'm person A. I just win one of the awards. So what's the probability of that? Think about, well, because it's a multiple stage. Okay, I give the awards to someone first, and then give to another person second stage. What's the best thing to use for this question? Tree diagram? Anything else I can use? Think about tree diagram. How long I will write? Table will be possible. Okay, which one is better? Think about that. Because tree diagram, okay, first selection will be 5 outcomes, right? And the second one will be 4 more outcomes for each, so 20 in total. So it will be quite long. Okay, it will be quite long. So I will use the table. Okay, let's say person A, B, C, D, E. Well, what I can do is I can say this column is the first awards, and the second the row will be the second awards given to someone. Is that a with replacement or without replacement question? Without. Okay, I select A and I can't select A again, so I will have cross here. Can't give to the same person. So how many outcomes do we have in total? How many? 16. Wait, 1, 2, 3, 4. Wait. 4, 1, 2, 3, 4, 5. 20, not 16. It's 20. 1, 2, 3, 4, and they have 5 columns, so 20 in total. Wrong counting, I think. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. It's a 5 times 5. Yeah, 20. Yeah? Not 16. Okay, which boxes represent A win awards? First column. Well, the cross already win 5 in a row. It's like the game. It's already win. Okay, so those circle means A win an award. Okay, either first award or second award, I don't really mind, but that's all the outcomes that A was involved. Okay, A was involved. So how many of that? 8. So the probability of A win is 8 over 20. 2/5. It's a tick. A will win, A will win, A will win, A win awards. A will win, A will win, A will win, A will win. Does that make sense? Do I change it to tick? Yeah. Okay, that question shows you that sometimes table is quite good. Okay, table is quite good. You can think about tree diagram and table, which one to select and which method use. This can be done by tree diagram easily as well. No, it's not that one. Can't. Only 2 awards maybe. Yeah, the tree diagram. But it won't be 5 people, I think. Yeah? Any questions, anyone? Anyone got any questions? No? Okay.